Sri Gurubhyo Nama children, welcome to online session. Already I have given introduction for coordination compounds. We have discussed the definition for coordination compounds, applications, and we have distinguished simple salt, double salt and complex salt. Up to that we have completed. Now I am going to start with the terminology used in complex compounds. The terms that are used in coordination compounds. To start with, the first one is coordination entity. The first one is coordination entity. A central metal atom or ion which are bonded to a fixed number of oppositely charged ion or neutral molecules are known as coordination entity. A central metal ion bonded to a fixed number of ions or neutral molecules, we can call it as coordination entity. For example, I have given the complex triamine trichlorido cobalt 3. Triamine trichlorido cobalt 3. So here cobalt is the central metal ion. Cobalt is the central metal ion. So the ligands here are chlorine and ammonia. So cobalt is central metal ion which is bonded to fixed number of ligands. When you talk about chlorine and ammonia, there are three chlorine atoms bonded to central metal ion and 3 ammonia molecules bonded to central metal ion. So this is called coordination entity. The next one is coordination sphere. The species inside the square bracket. The species which will be inside the square bracket, the central metal ion bonded to the fixed number of ions or neutral molecules. So the species which is present inside the square bracket, we can call it as coordination sphere. So usually in the square bracket, we will have central metal ion which is bonded to a fixed number of ions or neutral molecules. For example, potassium ferrocyanide. Here when you see the square bracket, so ion is there which is bonded with 6 cyanogen atoms. So here we can call this as coordination sphere. That is the central metal ion bonded by fixed number of ligands. We can call this part as the coordination sphere. Usually the ions in the coordination sphere cannot be ionized. So usually non-ionizable species will be in the square bracket. So in the coordination compound or complex compound, the species inside the square bracket cannot be ionized individually. So usually non-ionizable species will be in the square bracket. The next one is counter ions. Counter ions, the ions which are easily ionized. The ions which are easily ionized, that is present outside the square bracket. The ions that are easily ionized and which are present outside the square bracket, we can call it as counter ions. For example, tetramine copper 2 sulfate. The name of this compound is, there are 4 ammonia molecules. Tetramine copper 2 sulfate. Here when you talk about, we can see the species which is outside the square bracket. Sulfate ion is present outside the square bracket. The charge of the sulfate ion is 2 minus. So SO4 2 minus which is present outside the square bracket, we can call it as counter ion. The next one is cationic complex. So we are going to define what is a cationic complex. A complex or a coordination entity which has a net positive charge. When the complex or coordination entity has a net positive charge, we can call it as cationic complex. For example, hexamine cobalt. I have given example, hexamine cobalt. So here this complex has got a 3 plus positive charge. So outside the square bracket at the top, we can see towards the power, we can see the charge. So it has got 3 positive charges. So it is a cationic complex. Similarly, hexamine nickel. So here also there are 6 ammonia molecules bonded to the central metal ion. It has got the charge of plus 3. So both these compounds has got the net positive charge in the complex. So we can call it as cationic complex. Next we are going to define anionic complex. A complex or the coordination entity with a net negative charge, which has a net negative charge. A coordination entity or a complex ion which has a net negative charge, we can call it as anionic complex. For example, FeCN6 4 minus. So here when you see the complex it has got 4 negative charges. The complex has got a negative charge, so we can call it in the coordination entity. So we can call it as negative complex, anionic complex. So here AgCN twice minus, here also outside the square bracket above we can see the negative charge. The coordination entity has negative charge, so it is an anionic complex. The next one is neutral molecule or neutral complex. A complex which doesn't have any charge. A complex which doesn't have any charge, doesn't have either a positive or negative charge, we can call such a coordination entity or a complex as neutral complex. For example, COCl3NH3 thrice. So here you see the coordination entity, it doesn't have any charge. So it is a neutral complex. Similarly, nickel tetracarbonyl, this is also a complex compound which doesn't have any charge. So it is a neutral complex. Similarly, the other concept is central metal atom or ion. How to define a central metal atom or ion? An atom or ion to which the fixed number of ions or molecules, neutral molecules are attached. So an atom or ion to which a fixed number of ions or neutral molecules are attached, we can call such a species as central metal ion. For example, in potassium ferrocyanide, see the species inside the square bracket. The starting species is iron. So iron is the central metal atom here. So the ligand is cyanogen here. Both are inside the square bracket. The next one, ligand. The ions are neutral molecules that is bonded to the central metal ion. The fixed number of ions are neutral molecules bonded to the central metal ion is known as ligand. For example, NiNH3 6 times, so 3 plus. So it is a cationic complex or a defined cationic complex. Then the coordination entity as net positive charge. So this coordination entity or complex ion has net positive charge. So it can be called as cationic complex. Here the central metal ion is nickel which plus through oxidation state where the ligand is ammonia. So there are 6 ammonia molecules. So fixed number of molecules, there are totally 6 ammonia molecules bonded to the central metal ion. So ammonia is a ligand here. Now we are going to discuss about the types of ligands. There are different types of ligands. To start with, I am starting with unidentate or monodentate ligands. First one is unidentate or monodentate ligands. The ligand will have only one donor atom donating an electron pair to the central metal ion. So unidentate ligand, a ligand which has only one donor atom donating an electron pair to the central metal ion is known as unidentate ligand or monodentate ligand. So the ligand will have only one donor atom donating an electron pair to the central metal ion is known as unidentate or monodentate ligand. For example, monodentate, monoatomic, even in unidentate ligands there are monoatomic, polyatomic and neutral. Monoatomic Cl minus F minus, polyatomic Cn minus NO2 minus. Neutral molecules, it can be ammonia, water, carbon monoxide and nitrosyl group. So monodentate ligand is a ligand which has only one donor atom which can donate an electron pair to the central metal ion. So it can be a monoatomic, polyatomic and neutral. So monoatomic Cl minus F minus, polyatomic it can be Cn minus NO2 minus. Neutral molecules, ammonia, water, carbon monoxide and nitrosyl group. The next one is bidentate or didentate ligand. The ligands will have 2 donor atoms donating an electron pair to the central metal ion. So the ligand will bind to the central metal ion through 2 donor atoms. So we can call it as bidentate or didentate. So ligands that will have 2 donors to bind to a central metal ion, we can call it as bidentate or didentate ligand. Example, oxalato. So oxalato has got the formula COO. So here there are 2 donors. Here is one oxygen, there is another oxygen here. So each oxygen is donating a pair of electron to central metal ion. So this is one oxygen. Here again there is another oxygen. This oxygen is also donating a pair of electron and this oxygen is also donating a pair of electron. So it is an example for bidentate or didentate ligand. The other example is also there. Ethylene diamine, NH2CH2 CH2 NH2. So other example is ethylene diamine, NH2CH2 CH2 NH2. There are two donor atoms here. So this is a bidentate ligand where there are two nitrogen atom, each nitrogen donates an electron pair to the central metal ion. So we can call it as bidentate or didentate. So even in ethylene diamine there are two nitrogen atoms bonded to central metal ion. Each nitrogen donates an electron pair to the central metal ion. So we can call it as bidentate ligand or didentate ligand. The third one is tridentate ligand. So the ligand, in a ligand there will be three donors. The ligand will bond to the central metal ion through three donors. We can call it as tridentate. When a ligand has three donor atoms bonded to the central metal ion, we can call it as tridentate ligand. The very familiar example is diethylene triamine. The example for tridentate ligand is diethylene triamine. See, there are three donors. Here is one nitrogen, again there is another nitrogen, and again one more nitrogen. Three amino groups are there, triamine. Here one amino group, here one amino group, another amino group is here. So each nitrogen in amino group donates a pair of electron to the central metal ion. So here one lone pair of electron is donated. Here this nitrogen is also donating an electron pair. Again another nitrogen here is also donating an electron pair. So totally three donor atoms are there which is bonded to a central metal ion. So we can call it as a tridentate ligand. The next one is tetradentate ligand. When a ligand has four donor atoms bonded to central metal ion, so ligand will have four donor atoms. Each donor will donate an electron pair to the central metal ion. We can call it as tetradentate ligand. For example, they have given an example here. This is one ethylene diamine. This is another ethylene diamine. So here one ethylene diamine, again there is another ethylene diamine. It is bonded to central metal ion. So this ethylene diamine molecule has got two nitrogen atoms. So each nitrogen is bonding, each hydrogen atom is sharing an electron pair towards copper. Similarly towards the other side, here also there is an ethylene diamine. So each nitrogen is sharing an electron pair towards the central metal ion. So totally there are four donors. There are four donor nitrogen atoms which are donating four electron pair towards the central metal ion copper. So we can call it as tetradentate ligand. The next one we are going to see denticity and chelation. First I will discuss about chelation. Polydentate ligands which have more than many donors. The ligand which has many donors which are bind to the central metal ion, we can call it as polydentate ligands. So polydentate ligands have an ability to form 5 or 6 membered ring. So these polydentate ligands, they can bond to a central metal ion by a 5-membered ring, by forming a 5-membered ring or a 6-membered ring. So we can call it as chelates. So these compounds, they will form ring structures. So these polydentate ligands, when they are attached to a central metal ion, they will form ring-like structures. These ring structures are called chelates, and this property is known as chelation. So they will be asking you what are chelating ligands. So chelating ligands, the ligands will be joined like a claw it will be joined. So here chelating ligands are nothing but polydentate ligands which are able to form 5 or 6 membered rings with the central metal ion. We can call it as chelates, and this property is known as chelation. For example, copper is the central metal ion. Here both the sides it has got ethylene diamine. So here one side there is one ethylene diamine where 2 nitrogen atoms are ready to donate an electron pair to the central metal ion. Towards the other side another ethylene diamine, again another 2 nitrogen atoms are ready to donate an electron pair to the central metal ion. So here they will form ring like structures. We can call this as chelates, and we can call this ligand as chelating ligand. The next one, denticity. Number of coordination or ligating groups, number of coordinating groups in the coordination sphere, or number of coordinating groups or ligating groups, we can call it as denticity. The next one, ambidentate ligands. So ligands which can coordinate through 2 different atoms. there are two different positions in a ligand which can be bonded to a central metal ion. The central metal ion can be bonded to a ligand from where the ligand will have two different positions, two different atoms. For example, nitrito, NO2 minus. So we can call this as nitrito, where there are two different positions. Here nitrogen, through nitrogen also the linkage is possible, whereas oxygen, through oxygen is also the linkage is possible. When a central metal atom or ion is linked by a two different way in a ligand, we can call it as ambidendate ligands. For example, nitrito, there is a position through nitrogen also it can link, central metal ion can be linked to through nitrogen as well as through oxygen. Similarly, SCN minus, here again there is a two types of linkages are possible. The central metal ion can be linked either through nitrogen in SCN minus or through sulfur in SCN minus. So this way of linkage we can call it as ambidendate ligands. So once again, ambidendate ligands, where ligands which can coordinate to the central metal ion through two different atoms. So when you talk about nitrito, nitrogen is also a donor, oxygen is also a donor. So either the nitrogen will donate or the central metal ion will be attached either towards nitrogen or it can be attached towards oxygen. Similarly, SCN minus ion, here the central metal ion can be bonded either through nitrogen in SCN minus or through sulfur in SCN minus.